So in this video we're going to look at some standard networking and communication systems. And kind of like the controller video, we discussed picking the right tool for the right job. This applies for pretty much any application. So when you're trying to send data between devices, you want to make sure you choose the appropriate choice. So we're going to look at some of the differences there. So the first thing, there's a lot of terminology in these slides. Number one, protocol. Anytime you're talking about some sort of networking or whatever, you see this term protocol. Protocol is basically saying it's a set of rules, instruction, and methodology used so that when you're trying to communicate, both sides understand what information is being passed. We have a network, which is an interconnection of multiple devices for the purpose of transferring this information. So I'm going to use like information or data or packet. Those are all kind of referring to the actual information that we want to send. And so we can send that on a network where there's multiple devices, or we can send it through a communication bus, which there can also be multiple devices in there. So we'll look at a few differences of those. I also want to just kind of point out a couple other terms here. The node, if we talk about a node, we're talking about a device on the network or the bus that we want to communicate with. So we might have one other node. So if we're sending the data, we're a node on there also. But then we're going to send the data over this network to some other node, or maybe multiple ones. Also, just some other terms here. When we talk about a server, a lot of times people talk about a computer server. They think about a computer. But in reality, it's not the computer that makes it a server. It's the software program. So a server software program is a program designed to listen on the network, receive requests from clients, and then send the response to that request. When we're sending data, we can talk about broadcasting the data or sending it specifically to one or multiple nodes. So if we're broadcasting, what that means is we're just going to send the information out there. So I think of this as like a radio station. You're if you were a radio host and you're announcing or playing music or something on the radio, and you're just transmitting it out into the air, and you don't know whether there's one person listening to it or 100 or nobody at all. You really have no idea. You're just broadcasting. Where if you have a specific target, you could still technically just be sending it out there and not know, but at least you're sending it to one target. And then there's kind of the middle there where we have multicast, where you want to send it to multiple devices. This is very popular in online gaming, this multicast. So when we're sending this data, we want to talk also about the speed. So we can talk about the bit rate. The bit rate talks about how many bits you can send within a second, right? So you send 5 megabits, 5 million bits, or 1,000 bits, or whatever that rate might be. And then there's the baud rate. Now the difference between a baud rate and the bit rate is that we can maybe encapsulate multiple bits into our sending method, which we'll look at that a little bit later on when we get to frequency shift keying. But we can kind of incorporate multiple bits, and that'll lower the number of actual transitions we have to make, which maybe can allow us to send more data. So baud rate and bit rate, they're related, but they're not one-to-one. And then we have the bandwidth. So basically, the faster you send the data, the bigger your bandwidth. Okay. So if we're able to send, 10 megabits where somebody else can only send 1 megabit, our 10 megabit, it would be using a higher bandwidth technique to send the data. Now, if we have a electronic device on the node, or an electronic device, right, it's going to need power. And so they actually have come up with some different ways. The most common way is what's called PoE, or power over Ethernet. So if you have a low powered device, like say maybe a camera, then it's like, instead of having to run power to it and data to it, you can actually, there's techniques where you can send data and power both over that Ethernet cable. And then there's similar kind of things, people have come up with. It's like, well, we already have electricity there. Can I inject the data into the same copper wires that the power is coming through? So that would be power over data line. But these techniques allow us to simplify how copper wire or whatever we have to run to the device. Some other aspects of communication are, of course, timing. Okay, so timing can be just how fast you're sending bits, or that you're guaranteed that when you send a message, it gets there at a certain time or within a certain time. But when we send the data, especially if you think about we're sending a bit, okay, here comes bit 1, bit 2, bit 3, we can send these either with a clock signal, so that every time the clock changes, we know we're getting a new bit. That's called synchronous communications. And then there's asynchronous, where we send them at a rate, but we don't have them tied to a clock signal. But the ones where we have a synchronized clock signal, if our clock is not consistent, that's referred to as jitter, and obviously that can hamper communications. A lot of communication protocols also include something called a quality of service, which can be rated a couple of different ways. Sometimes it's rated as like a guarantee of delivery. Sometimes it's rated as error, how many errors were received through the transmission. So like I say, different protocols might rate this differently. If we're just sending 1 bit, we already looked at that in the previous class, right? We were just trying to turn something on or off. That was just 1 bit. And, so that's pretty simple. But when you want to group more bits together to send the data, we're going to group those into what's called a byte. And a byte is 8 bits combined. Now, it might sound like a lot when you first say it, 8 bits, but in reality, like, the maximum we can send is 255. So like if we wanted to send a number, we could send an integer value of 255, anywhere between 0 to 255. So there's 256 unique possibilities. So if we needed to send more data, we would have to send multiple bytes. And so we step up, we go from a byte to a word, which is 16 bits, and then what they call a double word, which is 32 bits, and then a quad word, which is 64 bits. Now, a lot of times nowadays, if people who don't work with different number-sized processors, they just work with 64-bit processors, they might call a word 64 bits. But, like our PLCs are only 32 bits, so when you're working between 64-bit machines and 32-bit machines, or even if you get to microcontrollers that might only be 16-bit, there's a bit of a distinction there between a 16-bit word and a quad word, which is 64 bits. But however you look at it, most of these technologies for sending data kind of group them together as a byte, but then they got to send, 2 bytes for a word, or 8 bytes for a quad word, or whatever the case is. You got to send all these bytes along. So now we get into the question is, okay, if I have a 16-bit word with 2 bytes and I'm going to send a byte at a time, which one am I going to send first? Am I going to send the high end, the most significant byte, or the least significant byte? And so again, this gets into the protocol. When I send it over to somebody else, they need to make sure that they're receiving it in the order that I'm sending it. So like Mac computers, for instance, they are a big endian, so they like to send data and store data on their computers and stuff. They store it in big endian format, where Windows systems, Intel-based processor, it's really the processor, it's not the operating system, they store it least significant byte first. And so you just need to understand how your data is ordered so that you can process it correctly. Now, when we get to really large blocks of data, we need to separate it. You have like lots of different things where maybe you're sending out, like we looked at with the weather lab, you're sending out temperature, wind speed, wind direction, pressure ratings, all that information that is sent out. So now you got to understand how you got to package it and send it out, and the person receiving it needs to understand how it was packaged. So like what we used for the MEDAR data for that lab is we used a string, and they weren't actually fixed length strings, but they were a string of data, and then we had to go in and pick out those pieces. They also have what they call delimited, where you could have like a CSV file. So if you've ever worked with Excel spreadsheet files, they have what they call a text-based file, which is a comma-separated value. And so that sounds pretty good when you put in commas to separate the different pieces. The problem with that is that normal text, we use a lot of commas in it. And so therefore you got to put commas and quotes in there, and it actually kind of complicates it. So sometimes we see a pipe delimited file. The pipe symbol is a symbol usually on a standard keyboard is on the key with the backslash character right above the enter key. And it's a vertical bar with kind of a usually a 2 like vertical dashes there as it appears. But the thing is we never use that in ordinary text. And so it makes a better delimiter for simple delimiting text, because there's not going to be any commas, so you don't have to worry about throwing quotes around things. But when you get even more advanced, you get into what's called JSON formatting or XML formatting, which gives you a lot of flexibility, because now you can send the label, maybe a description, and the value. So you can send multiple different pieces, and they're formatted in a much more structured way, and you can very easily parse and send data. All right, so we talked a minute ago about broadcasting the data, and there's this concept of state where when you broadcast the data, it's kind of like I said before, you don't know whether anybody's listening to it or not. So state communications, we have state or stateless. So if it's stateless communications, it's kind of like the broadcast, where you don't know that they're out there. Even though you may only be sending it to one person, you just kind of send it and hope they receive it. Where if is state communication. What you're going to do is you're going to first establish a connection. You're going to get an acknowledgement back from whoever you're sending the data to, and so you know that they're ready to receive the data when you send it. So when we're sending our data, it kind of goes back to the other slide there talking about how the data is organized and stuff. There's overhead in sending the data. And again, these different protocols, there's some protocols that have virtually no overhead at all, and then other ones that have a ton of overhead. So to kind of give an example what I mean by overhead, I use this analogy here. So let's consider that we're going to drive to or go to Washington, D.C. to the White House, right? You know, the president's invited us for dinner, so we've got to get to the White House. And so we have one of two options, right? We can just jump in the car and start driving. Well, I looked at Google. According to Google, it'd take about 5 hours and 58 minutes, you know, call it 6 hours to drive to Washington, D.C. On the other hand, if we wanted to fly, I looked up the flights, and we could get a flight from the Akron-Canton Airport to the airport in Washington, D.C., and it's only an hour and 20 minutes instead of 6 hours. However, now you got to kind of think about it. It's like, well, I'm going to have to buy the ticket. So usually, you know, I'm going to search online and try to find the best price for the tickets. Then I'm going to have to drive to the airport and park and then walk. Then, you know, they always tell you got to wait. You got to get there 2 hours early so that you know you get through security in time. Most of the time you get through security and then you're sitting there for 2 hours. But, you know, they always tell you, and I have been in some airports at times where I got there and security was so crazy that I'm like, I'm going to miss my flight, even though I did have 2 hours. So, you know, if you've traveled much, I'm sure you understand that. And then if I sent some luggage or whatever, I'm going to have to wait for it to be unloaded and set out so I can get it. And then I'm going to have to find a cab or an Uber or something to get traveled over there. So if we add all that up, you know, just using these values I put in here, it's going to take us 5 hours and 22 minutes to fly. So, you know, if you look at all that, it's like, well, we're not necessarily saving a whole lot of time. However, you know, if we were flying to, I don't know, say somewhere like, you know, California, Los Angeles or something, you know, it's going to take way longer to drive that. So these, you know, these extra 4 hours of overhead, you know, still apply. So you have the same amount of overhead, but, you know, if I'm going further, then, you know, it certainly makes it worth it when you consider, you know, trying to drive to Los Angeles, if you're just looking at the time aspects anyhow. So that's kind of the idea here with, again, overheads and picking the right tool for the job. You know, when you're sending lots and lots of data, this extra overhead doesn't really cost you a whole lot in time and effort. So when we're trying to use these different communication protocols, you know, the programs we're going to use have what's called an API, or application programming interface, which is a, you know, again, it's basically a set of rules and things that we have to use so that we can give it the information that we need to get the data where we want. So typically most of our programming tools that we're going to use will have a library that has already been written for those APIs. So all we have to do is just figure out how to work that library, that set of function calls, and pass the data as needed to set up the communications. All right, so when we were talking about controllers, we talked about this concept of real-time control. But if our controller is going to be communicating with other devices across the network, we also got to apply that real-time to our network. And so we can have hard real-time communications where we're guaranteed that the message is going to be delivered within a certain amount of time. And then we have what I consider soft real time, where the data is going to be sent over there, but it might get delayed along the way. All right, so when we're talking about that overhead, this slide probably should have been up one here, but we're going to look at the MQTT protocol here in a little while. This is a very lightweight, has basically no overhead at all. And then there's the REST API. Now the REST API is basically what we use anytime we use a web browser to search the internet, to go to Google, Amazon, watch this YouTube video, whatever the case might be. It's got a lot of overhead, but that overhead provides a lot of functionality, where MQTT is great for passing little bits of information, but and it has virtually no overhead at all. But it has its limitations there also. So let's look at some different categories of networks here. So we'll look at topology and then some timing and transmission methods. So for topologies, the first thing we could have is what we call the point-to-point. So point-to-point is very simple. It's not technically, I guess, a network at this state. You're just connecting a wire up to another device, and you want to communicate with that. So for this slide here, we're going to consider, I want to send data. I'm at point A, and I want to send data over to B. And so with point-to-point, I just, connect up my cable and transfer. So we did this with our BeagleBone, right? We plugged in the USB cable, and we were able to communicate between our PC and the BeagleBone. We can also have a bus. So in the bus, you basically just have effectively maybe one cable, but you, instead of just having the two unique devices on it, you can have multiple other devices on it also. Now for standard Ethernet, we use the star design. So in this star design here, what you have is you have what's called a hub, and actually nowadays it's usually a switch. And it's a center point. So A up here, when it wants to send data, it sends the data to the hub, and then from there, the hub has one of two choices. If the hub understands that the data we're sending goes to B, it could send it directly to B. We'll come back to that. But if the hub doesn't understand, all it does then would be broadcasted out to all of these. So D, C, and E are going to get the same message. But the message is addressed to B, so what happens when D, C, and E get it, they just ignore it. Because they're like, well, okay, I saw this message come in, but it's not for me. I'm just going to ignore it. Now, on the other hand, there's a ring topology. This was very popular back in the 90s. They had something called Token Ring, which was at that time was faster than Ethernet. So the idea here is you want to send a message to B, and so you're connected to C and D devices. So you can send the data to clockwise to D, which has to then pass it through E to get it to B, or you could send it from C to B. Now the nice thing about this though is if you had a break between A and D, you still had connection. You could still get a message all the way over to D because you basically had redundancy. You had two paths. Now, what's gotten very popular in the past 5 or more years is what we call mesh especially for wireless applications and stuff. And the idea of the mesh, it's kind of like Token Ring, only you have even more. So I'm sitting here at A. I want to send my message to B, and B's out of range, or I'm not directly connected to B, so I need a different path. So in this case, I can send it to maybe D and C, and or both of them, and then they will pass that message on. So D might pass it to F and to E. So and then C is, could pass it to E and F also and stuff, and they pass it on until it finally gets to B. So for wireless technologies especially, this is very nice because you only have a limited range, but if you can pass it on to these guys that are closer, that effectively extends your range, although it will delay the communications because it has to be repeated multiple times. Alright, so if we're just doing standard Ethernet, we need what's called an Ethernet cable. Now typically this is a Cat5e cable or a Cat6. And what these are cables. So there's 8 conductors, there's 8 wires in here, and they come in colored pairs. So you can see there's orange, green, brown, and blue, and there's like a orange, white, and green, white, and so on. And these are twisted together to prevent what's called crosstalk, to minimize interference as data is being transmitted on these different pairs of wire. So the Cat5 was the standard. It was good for a gigabit, and then they've come out with Cat6, and they even have Cat7 and 8 now, although Cat5 is actually still used an awful lot for communications. Now at the end of an Ethernet cable, we have what's called an RJ45 connector. So this connector here is a plastic connector with a little locking tab here. So when you try to disconnect it, don't forget to press that little tab and disconnect it. But when you look at the cable, they have what they call an A and a B wiring here. And so the A wiring has green, white, and green, and then brown or orange, white. Where the B starts at orange, white, orange, and then goes to green. And so when you try to connect this up to a network, you have to make sure that you select the correct one. Alright, so if you have a B to B type of connection, so you have the orange, white, orange at the left on both of your jacks, that's called a straight through cable. And you need that if you're going to do the star communications. On the other hand, if you have one that has the green, white, green A, and then the orange, white, orange on the other end, that is called a crossover cable. Now this is important because if you take your laptop, for instance, and you want to plug this into the PLC and download a program to the PLC. So you take your cable and you plug it directly from your laptop into the PLC. You need a crossover cable. The reason for that is because it transmits on one set of wires and receives on the other. And so you may need to make sure that the remote device, if you're transmitting, your transmit wires are connected to the receive wires on the other device. And that's what the crossover cable down here is doing. I've actually got these crossed in the slide here. So the crossover is crossing these and putting the receiver wires on the other end. So if you're transmitting on green, your green needs to be then going into the receive connection on the remote device. However, if you have a star type of hookup, then what's going to happen here is one of the things that the hub or the switch does is it does the crossover for you. And so therefore you actually just use a straight through cable. Now, if we're going to send our information, we need to send it directly. If let's say we're gonna send a thank you letter to the president after we got back from our dinner, and so I'm gonna write out a thank you card or whatever and mail that to the president. Then I need to take my thank you card and I need to encapsulate that, right? So, and there's multiple layers of this. So think about putting a letter or a thank you card or whatever in an envelope here. I'm going to address this to the president, and then from there is going to be picked up and put into a mail bag. That mail bag will then be put into a mail truck. It'll be then taken to Washington, D.C., where it'll get sorted, go into the mail truck, go into the White House, and then go into a bag to get carried into the White House, and then get separated out. And finally, right, the president's going to open this letter himself. I'm sure he wouldn't have anybody else open a letter addressed from me, and get that data or that information or that thank you card or whatever it is that I had put in this envelope. So, but this is this concept of encapsulation. So we have a packet is the data that we want to send, but we're going to have to pack it up, put addresses and all this information on it so that it gets to the correct location. Now, when we're sending data, we can send data using what's called simplex communication, which means that we're just sending it out and we don't, we're not going to get anything back. So it's one-way communication. That's called simplex. Or we can do duplex. In duplex, we can send data and receive data, but we have what's called half duplex. If you're doing half duplex, it means that you basically have one set of wires and you can only send data while the other is listening. And then when the other node wants to send data back, you have to stop and listen. But if you do full duplex, you can actually be sending transmission and receiving transmission at the exact same time. All right, so looking at this concept of encapsulation, there's a couple of different models of how the data is encapsulated. So there's what they call the OSI model here, which breaks it down into 7 segments. But if you look at this, you see the green segments here. There's 3 of them. And then the orange and red down here. If we look at the other model, it's a little bit simplified. It basically took all 3 of those top layers and just call it application, and they're done with it in the TCP/IP model. And then the Ethernet has both the data link or the addressing, the physical addressing, and just the physical medium kind of thrown in together. So, but both of them have the transmission control or TCP or simply transport layer and the IP layer. All right, so this lower layer is the hardware. This is the physical way we're sending the data. So whether we're sending it over copper wire, fiber optics, or wireless. Okay, so that's your physical thing, and you need a physical address for that. Okay. And then there's what we call the internet layer or internet protocol layer, and there we also have an address, but that address is specifically for it's a logical one, which means that it can be changed very easily on the fly. So the hardware ones mean that they're actually kind of set in the chips. And years ago, when you bought it, it came with a hardware address and you could not change it. Nowadays, a lot of newer systems will allow you to change the hardware address after the fact. Some of them still don't. But they have that physical hardware address that, like I say, on a lot of systems like your PLCs, you can't change those. But they have to be unique for everything on the network. And then we have the internet ones. Those have to be unique for everything on the network also. And then there's the transport layer. Now the transport layer is basically all inside that one computer. So if you think about it, like the analogy of this is like classrooms at the college. So we have Stark State College, and it's full of all these different classrooms. So if you're trying to send data to the college, well, you send it to 6200 Frank Avenue, that's our college, but where's it going to end up at? Where the transmission control protocol now basically specifies the port, what we call it the port in networking, the port value, but you can think of it as like the room, C205 at the college. All right, so when we send data across the network, again, especially in Ethernet, they refer to that as packets. And so you're going to send this packet of information, but you've got to address that packet. So this is that overhead stuff so that we can get it sent to whoever it's supposed to go to. So we have to both put the sender's address and the return address. Sometimes the information that we're going to store in there is also referred to as a payload. We kind of saw this with our Node-RED on the BeagleBone. It uses this term payload a lot. All right, so here I am. I'm going to send a letter to the president and let him know what I'm thinking. And so I have to address this, right? So this is this encapsulation here. So I have to, put who it is, where they're at in the White House, and then where they're at in Washington, D.C., right? So they're on Pennsylvania Avenue, house number 1600. And then, of course, the first thing the president is going to do when he gets this letter is they're going to reply to it and send it right back to me. So I need to make sure that I include my information, my return address information, so that the data can get back to me correctly. So when we look at this encapsulation, we have these different layers here, and I just want to use this analogy so you can kind of understand the differences here. So basically, the 1600 Pennsylvania Avenue, that is the network layer. Now notice there's two parts to that. There's the number 1600 and then the street, right? So there's a lot of houses on this street, or buildings at least, right? Businesses or something on Pennsylvania Avenue, and not just the White House. And so 1600 is the White House specifically on that street. So when we look at IP addresses here in a little bit, keep that in mind there. And then the West Wing, right, is the location of the Oval Office. So that's where inside the warehouse, right, or the White House, I don't want my letter going to the kitchen staff. I want it to go to the president in the West Wing. So that's that port number that we talked about. All right. So we have like the physical address, which is kind of the MAC address. I guess maybe you could think of that as like the physical post office in Washington and here in North Canton. You could kind of think of that as the physical address. That this is where we have the trucks and the mail sorters and the staff who receive the mail and sort it and deliver it and all that. So we have our physical layer, layer 2, and then we have this logical address, layer 3, and then the port number, and then basically the applications are tied to those port numbers. But one application like your web browser, right? If you use like tab web browsing, you might be on multiple websites. Each one of those would have their own port number to make sure that when the data comes back to your web browser, it gets put in the correct tab. So this just shows the layering actually with the hardware at the top here. So we have what's called the MAC address or the hardware address, or also it shows up as physical address on some commands. This is the 48-bit physical address that's built into each device on an Ethernet network. And so an example of this would be like room C212 or room C205 in the classroom. So it's a physical room on there. This is layer 2 of that OSI model that we've been talking about. And then we go to the next level, which is layer 3, which is the IP address. So if we compare this to, say, the college here, 6200 Frank Avenue. So we have the street address, and then we have, or the street house number, and then the street itself. So there's two parts to this address, this IP address. And so we'll look at that in more detail in the next few slides. And then there's the port. So if you think about like a room, you're in room C205 or room C212 or whatever room, that's the physical room. But then within that room, you would be at a port or a desk. So the IP addresses, there's IP version 4 and IP version 6 of the IP addresses. And we use primarily for internal networks, we use IP version 4. And they break this up into multiple classes, the Class A, Class B, Class C. And within those classes, they have private addresses. So if you look at, say, Class C, so if you know what your home network is, you probably have something like a 192.168.0. something. Well, the .0.0 is actually the network. And then you would have devices on that network. The Class A starts at 10. And so you have a 10.0.0.0 is the network, and then it can go all the way up to 10.255.255.255. So this IP address is 32-bit, like it said on the other slide, and it's each of it is broken down into a single byte, right? So 32 bits is 4 bytes, but then it breaks it down into what they call octets. So we have these 4 different parts, 8 bits each. So we have a subnet mask here. So for Class A, the subnet mask for that is 255.0.0.0. Now the 255 means that's the first 8 are all ones. All right, so 255 is 8 ones in binary. And so sometimes they write that as a /8. The Class B network starts with a 172 number, and it has the first 16 bits are part of the network. And then the Class C, the first 24 bits are part of the network. So what that means is that with a Class C network, you only have 8 bits that can be used for individual devices. Now remember, for IP addresses, you need a unique number for each device on the network. And so that unique number, you only have 8 bits for that, and 2 of them are already used. So the .0 is used, number 1, and also the 255, which is the used for broadcasting to everybody on the network, is used. So you lose 2 IP addresses out of the 256 available. So for a Class C, that gives you 254. Now, if you use a Class B addressing, then you can get up to 65,534 devices all on the same network. And if you really needed it, you could do a Class A network, which would give you over 16 million on the same network. So those are the different classes, but you tend to see, especially in home networks, this 192. If you go out and just buy a Wi-Fi router, it'll give a 192.168 value, which is a Class C private network. So this IP address, again, there's 2 parts to it. There's the network, which is set by the subnet mask of all ones, and then there's the host, which is the unique device on that particular network. So every device on a network has to use a unique address. Now, you could have another private address in another area that could use the same number, but they can't be on the same with the same unique host address. So this subnet mask is the key to defining what is a network. So here's an IP address, 10.15.24.5, and then /16, where the /16 is saying the first 16 bits are the network. And then I have a second IP, which is 10.15.23.56. Now, since these are both using a /16 or a 16-bit subnet mask, it says that they are on the same network. However, if we look at this slide, I got the same numbers, but I'm using a /24. And so therefore the red is the network now. So the top one is on the 10.15.24 network, but the bottom one is on the 10.15.23 network. And this is where the crossover cable gateways come into play, because if you were to do a direct connection, so if you were to do a direct connection of your laptop to the PLC or the BeagleBone or whatever with a crossover cable, these two, your PC had the top address and the other device had the other address, but the /16 says they're on the same network. So a crossover cable with a point-to-point connection will work and you can communicate. However, even though you have the same working cable, if you use a /24 for these 2 IPs, they're on separate networks, and the 2 devices cannot communicate. Even though you have a direct connection with a valid working cable, they'll think they're not connected. All right, so that's where this subnet mask becomes very important to make sure you have it correct. All right, so some other devices, we talked already about this star topology here, right? So you have a switch or a hub that you connect to. This is for like a local area network. So everybody connected into this network can then communicate with each other as if they're on the correct network, as long as their subnet masks and everything are correct. However, if you want to get to a different network, so if you have a device on a different network, then you need a router to be able to route from the current network over to another network. So a router actually has to be connected to both networks, and then it's your path or your gateway to the other network. So the router is basically the physical device that provides that gateway to the other device. Now, normally there's what we call a default gateway. This is the one that'll get you to any general network. But you can have, like, say, a couple of different private networks, and then you could have a router that was set up to just allow you to go from private network 1 over to private network 2, and then you might still have a general gateway to get out to the internet. And then we have something called a firewall. So the firewall is basically a piece of software. Again, it says device here, but technically it's the software. So any sort of computer device could be set up with a firewall. Windows actually has a firewall software program that you can set up to put a firewall directly into Windows, for instance, and any other major operating system can do that. But normally we just have this separate device, which is usually the gateway, the default gateway also, which gives you a firewall to prevent unwanted connections from outside your network from getting in unless they meet specific requirements. All right. Now the thing is with PLCs and robots and other devices like that, they are not designed to be hooked directly to the internet. They do not have any security on them. So you need to make sure that when you set up an industrial network, that it is separated and you got a firewall and everything, and you're protected from other networks, right? So this is an internal network that you want to have and make sure it's secure. All right, so let's talk a little bit here about wireless communications. Of course, you've heard of Bluetooth and Wi-Fi. RF just stands for radio frequency, and then LTE is cell phone. And then there's some other long-range, low-data ones that are available. Now, when you try to send binary information, and wirelessly, basically what you have is you have a transmitting frequency. So you transmit on a particular frequency. So this top sine wave here shows the transmit frequency. And then to send a 1 or a 0, you can do either frequency modulation or amplitude modulation. So the idea here is if you do amplitude modulation, that's actually shown down here. So notice like this value on our main frequency is a 1. But down here at the amplitude modulation, it's actually peaking at 2. All right, so to make it a 1, we've amplified it in this example by a factor of 2. And then when we want to send a 0, we reduce the input. We reduce the amplitude down to a half. And so in this way, we can clearly transmit a 1 or a 0 by looking at the intensity of the waveform. There's also what they call frequency modulation. And frequency modulation, what you do is you change the angular frequency of the sine wave. So you can see here in each block there's one full sine wave in the transmit. But when I do frequency modulation, then when I want to send a 1, I double the frequency. And then when I want to send a 0, I have the base frequency. And so in this way I can send 1s and 0s and clearly be able to receive them on the other side. So those are the two things. I'm sure you've heard, of like radios. You have FM radios and AM radios. So this is a simplified view of kind of how that is performed. They also have what they call frequency shift keying. And so the difference here is if we look at the center, this is our frequency modulation we just looked at on the other slide, and we were able to send in 4 blocks we were able to send 4 bits of information. But if we do something like phase shift keying, what we can do now is instead of just doubling the frequency, if we can send like say 1 1, by in that same amount of time. So we basically quadrupled instead of doubling the frequency of the sine wave. We're able to send 2 bits in this same block. And so you can now send, in the same amount of time, I'm able to send different values. Okay, so I'm able to send twice as many bits as I was with just base frequency modulation. So phase shift keying is frequency modulation, but it's taken to a higher extreme. And again, this is just simplified examples here of how this is done and so this gets into what I talked earlier about baud and bit rate. So like this one, we're sending bit, but here we're grouping those bits, and so we're able to send it better, and so that's kind of where that term baud rate comes into play, although baud rate doesn't necessarily refer to wireless transmissions. All right, so this LoRa, you can buy these ESP32 devices for this. There's pretty cool. The cool thing about LoRa is it's good for extremely long ranges. All right, so I have a little chart here just showing some of the basic wireless technologies. So up here we have Wi-Fi, and at the top of this chart here you see the speed. So you have Wi-Fi and cell phone, right, can transmit lots and lots of data very fast. However, the range of Wi-Fi is only, maybe 100 feet or something, and you start running into problems. Bluetooth is even worse as far as distance and the speed. So it's not as fast as Wi-Fi, and the distance of it is also smaller. This chart, they look like they're the same, but really Wi-Fi can go further. And then we have this thing called LoRa and a couple of other wireless technologies that are available that can actually go out a couple of miles depending on your antenna and obstacles in the way and stuff. But notice that they can't send a lot of information. So they can send it a long way, but they can't send a ton of data at a time. Now, when we talk about industrial networks, there's lots and lots of different networks that have been set up to do communications. And one of the key things about these, right, since these are for industrial controls, they focus on real time. And the 3 most common that you're going to hear about and see nowadays, I mean, there's a lot of these other ones are still in use, but the three big ones listed here we'll talk about on the next few slides: Ethernet/industrial protocol, Modbus TCP, and Profinet. All right, so Ethernet IP is probably, especially here in the United States, about the most common. It uses standard Ethernet equipment, so you can just, like, you could literally go over and buy a router over at Best Buy and bring in and then plug in your robot and your PLC and everything else into this switch, and they can communicate. All right, so when we're doing IP testing, there's always some testing tools to kind of verify your setup. So on Windows, we have something called ipconfig. So if you run ipconfig or ipconfig/all, it will show you your IP settings for that machine. Ping is a command that you can run that will allow you, if you know the IP or the name of a remote device, it'll allow you to send a ping or a packet of information over to that other machine, and then it will respond back. This is a nice tool because it can verify that the machine is powered on, your wiring is correct, and your IP configuration, including that subnet mask, are correct. If you don't get the ping, something is wrong. But if you get the ping back, then you know that all those things are correct. Now, one thing I will say about ping is that it can be turned off by devices and by routers and stuff, so it may not always work. All right, so then we have the NetStat. So NetStat will show you those ports on your local device. There's also another tool, Telnet, which a lot of times isn't installed on Windows machines, but you can get like a download version that'll run without installing, called PuTTY. And Telnet is technically it's a communication tool where you can log in and run commands, text commands. So you can run these text commands or text connections. But what's as a testing tool, Telnet is kind of handy because it'll allow you to specify the port. The ping command up here will tell you that the device is there and that layer 3, the internet layer, is configured properly. But it doesn't tell you about that transport or port layer. The Telnet will allow you to actually specify the port, and if you make connection there, then you know that the port is also correct. And then there's another command which is kind of handy called the ARP. This is Address Resolution Protocol, and this will show you the mapping between that physical hardware or MAC address and the IP addresses for all the devices on your local network. Okay, it's only good for your local network, but you can see all those devices, what their hardware address is, and what their IP address is. A lot of times when you get like a new PLC or whatever, it'll have a little sticker or something showing its physical hardware address. And so if the PLC is set up using something called DHCP, which is dynamic IP, and you plug it in the network, you don't know what its IP is. But this ARP command, if you're on the same network, the ARP command then can be used because you can find that hardware address with the sticker and then connect to or then view what the IP address is. All right, on Linux devices, especially like our BeagleBone, okay, our BeagleBone has a service on it running on port 80 called Cloud9. And what this will do is this will allow us to get a shell or command line interface into the BeagleBone to test or modify networking if we need to. Now, to do that, the first thing you have to do is get root privileges for most of these commands. So you type sudo. Sudo is kind of a command thing that says run as the super user, which is what they call the administrator. It's also known as root, R-O-O-T, on there. But so this sudo command will allow you to do that. Now, when you do that, it'll prompt you for the password. And we haven't changed the password on the BeagleBone, so it's the default, which is just temppwd. All right, so one of the simplest things to do to get super user access is you type sudo, which will run one command as super user. But if you choose that command to be the super user command, it will then give you full administrator or root access to the system. So when you run the rest of your commands, you don't have to keep typing sudo. You don't have to do this, but it saves you typing sudo space every time. Now on Linux, the configuration command of your IP is IF, and the F here stands for interface, so hopefully that'll help you remember that. So on Windows, it's simply IP for Internet Protocol, but on Linux, it's IF for interface, network interface. And then they still have the ping command. They have a route command, which will show you your default gateway. And if you need to change a DNS, one way of doing that is through what they call the etcresolve.conf file. And you could force, this command forces in the Google default DNS server into that configuration file. So if you're having DNS issues, that's one way to correct that. Right. Now, IoT stands for Industrial Internet of Things, which I'm sure you've probably heard of that term. And there's a lot of common protocols and stuff that are used within this in here. So there's several bus protocols, and we've seen when we looked at the pinout of the BeagleBone, we saw some of these listed, like this I2C and this SPI. These are bus protocols that allow us to send data. There's also a very simple one called OneWire, which basically says that the power and data are on one wire. You still need a ground wire to complete the circuit. So OneWire is kind of cool. It's a digital communication bus, and you can buy lots of different devices that use this. And you just need one pin on your BeagleBone or Raspberry Pi or whatever, and you can connect a lot of different devices on here, because each device that you connect will have a built-in 64-bit unique address on there. These things, this OneWire protocol is actually used on virtually every laptop and computer, desktop computer, that they have temperature sensors in them, and so they actually use this a lot in those. If you're trying to set up your own, so you can buy these all kinds of different devices that use this OneWire protocol. The only catch is you just need one 4.7 kilo ohm pull-up resistor on that network. Some other buses, probably the most common, this one's been around, I don't know, since the 60s, if not before, is RS-232. And this demonstrates what I kind of talked about a little bit before with simplex and duplex. If you have your first device and it's transmitting, you need the transmit wire to connect to the receive port on or pin on the other device. And then when the other device tries to send you data, its transmit needs to be connected to your receive. So you need what's again called a crossover cable to do this type of wiring. If you're using an actual RS-232 type cable, you need to make sure you have one that does this crossover. Another one that's very popular is RS-485. Now these first buses that we're talking about, these are slow. These are not designed to send tons of data. It's not like you could watch a YouTube video on these buses. They're designed to just send information like temperature data, pressure data, things like that. So the RS-232, as we saw, is basically a point-to-point type of connection, but the RS-485 can be point-to-point, but you can actually just keep wiring in multiple devices. So you can actually wire up a maximum of 32 different devices on that and communicate your data across that with all those devices. The CAN bus is very popular for automotive and airplane use. Okay. And then there's this Modbus. So Modbus was created by a PLC manufacturer called Modicon, and it's very similar to the other two. It's not used that much, but the Modbus TCP is. So we'll get on to that. And then there's also the Profibus, which again is kind of evolved into Profinet. Okay, so with when you think about these OSI layers or network layers that we've been discussing here, so again, these are real time, and so what they do is they skip over some of these layers. So these extra layers are like overhead. They add in extra overhead like I was talking about earlier. So if you can skip over them, then you can reduce you can basically improve the communication time. All right, so we'll see that as we look at some of these other ones here. So GPIB is the general purpose interface bus created by National Instrument. Well, I guess it was created by HP, but it's used extensively by National Instruments here. And those are the white boxes we have on the benches in the classroom, allow us to connect through a network to those white devices, and then we can connect in to oscilloscopes and other test equipment using this bus. All right, so there's a lot of these newer networks that utilize the Ethernet base on there. So the first one of these we'll talk about is Ethernet/IP. So Ethernet/IP means industrial protocol. And then there's a couple other ones, Ethernet PowerLink, and then Ethernet CAT. And then there's Profinet and Modbus TCP. Okay, so I think the three big ones, like I marked on that other slide, are Ethernet IP, Profinet, and Modbus TCP. Now, when you look at the speed of these, this chart's just kind of showing some information, but the big thing here to kind of like look at the speed. So what you have with Ethernet/IP is you send a clock signal every, say, about 1 millisecond. All right, so this is Ethernet/IP is actually kind of slow compared to some of these other ones because it uses the clock signal through the application layer, which we'll look on another slide here. But and then what you want to do is you're going to send different data. So let's say we're sending out data from our PLC to 3 different robots, and we're telling them how fast to go. So we'll have like spot 1 will be the speed for robot 1, spot 2 is for robot 2, and 3 is for the third robot or whatever. And so what we do is we lay out this is all the information, and we're going to send this out every millisecond. So every millisecond we're going to be sending the robot speed updates. Now it might be the same speed it was last millisecond, or maybe we're going to say speed up a little bit or slow down a little bit. But that's the scheduled phase of data that we're sending. Now the Surcos is kind of the same thing. It sends a clock signal here, but it provides for a scheduled phase and then an unscheduled phase. So the idea is you have your speed for your robots coming every millisecond or whatever, but then it also saves some time to send some data that is not repetitive coming every so often. Now, what I want to like with this slide here is just to illustrate the speed difference between the Surcos and Ethernet IP. So Ethernet/IP in an industrial protocol can send updates about every millisecond, which most of the time that's way fast enough. And honestly, most of the time the default is usually 50 milliseconds. So it's not really all that fast. But if you need really high speed, the Surcos will let you get down to 3125, and this EtherCAT that I mentioned, this is about the fastest I've seen. This will let you send updates every 12.5 microseconds. So it's extremely fast. So why is it so fast? Well, like I mentioned before, what part of the reason it's fast is that it actually For the high-speed stuff, it skips over these layers. Okay, so it skips over the IP layer and skips over the TCP layer, and so it just goes from the hardware directly to the application, skipping over these extra layers. And so that is one of the things that make it so fast. The other thing is you can't go over to Best Buy and just grab a switch or a Wi-Fi router or whatever off the shelf at Best Buy and bring it in here and plug it in and do EtherCAT communications. It requires that switch to have special hardware. All right, so the problem with the switches and things that you would get from somewhere like Best Buy is that they're Ethernet, and Ethernet was intentionally, when it was created, not to be real time. It was designed to allow multiple communications, but the concept was that, well, if two people are trying to talk at the same time, one of them, they have what they call a collision, and then they both go back and they randomly wait a random amount of time, and then they try to transmit again. And the hope is that they both choose two random times before they try to retransmit. And this is how you can have multiple devices transmitting all on that same hub or switch. So every time there's a collision, they both just go back and they wait a while. So it's actually intentionally not real time. So to do EtherCAT, to get it down into that 12 microsecond range, they had to actually modify the physical Ethernet switch to maintain the speeds that they want. Profinet for real time does the exact same thing. It has this down here at the Ethernet layer. They physically made changes to the physical hardware, so you can't do real-time data with Profinet with off-the-shelf hardware. You got to buy specialized hardware, which of course increases the cost. It also again skips over the IP and the TCP layers to help improve the speed. Ethernet/IP, on the other hand, they went about the solution in a different way. What they did was they put the clock up here in the application layer, and they still go through all these layers to get there. And so in a way, it's not true real time, because down here at the hardware level at Ethernet, again, Ethernet was designed not to be real time. However, Ethernet is so fast that they run the clock here and they can reliably do real time down to 1 millisecond. Again, they can't go as fast as EtherCAT, but they can go fast enough for 95% of all applications. There's just EtherCAT comes into play when you have things that are extremely high speed, and Ethernet IP isn't fast enough. But for most standard industrial applications, this works very nice, and it's basically real time. Within a millisecond, based on that clock signal, or like I say, a lot of times it's really more like 50 milliseconds, that the data is going to be sent and received in that amount of time. All right, so the Modbus TCP kind of does the same thing. You can use standard hardware and switches with the Modbus TCP all the time. Okay, but for the real-time piece, it's done through what they call the SIP layer. So it's kind of bypassing most of these other layers so that the data can be sent very fast and not delayed over here. All right, so here's just a chart. This one's actually kind of gotten old now. I need to find an updated chart of this, but back in 2018, about 27% of the devices on the network were using Ether IP, and 29% were using Profinet. 6% were using EtherCAT, and then some of them were just using Ethernet TCP/IP. Now, TCP/IP is not real time. It's just a standard network that you have when you just go in and plug in your laptop and try to watch YouTube videos or whatever that you're going to do. So this is not real time, but again, it's so fast that a lot of times you can get away with the fact that it's not guaranteed real time. And then here's some of the other ones listed over there, like Modbus was only at 7%. So the bulk of it was either Profinet or some form of Ethernet. This slide is just showing the response time and the maximum allowed jitter time for each of these protocols. Alright, so let's just take a minute or two here to talk about wireless technology. So of course we have Wi-Fi and Bluetooth, and then we have the long range on here. And so the Wi-Fi is great because it can send tons of data very, very quickly. But there's a cost for that. So if you're running this off of a battery, right, it's going to reduce your battery life very, very quickly. On the other hand, if we use some of these low power ones like LoRa, it's very low data, but it's also very low power. So if you just have a remote sensor sending temperature data or pressure, weather data, and you just have it like mounted far away, you can, but all you're doing is just sending these few updates every minute or every few seconds. You can get a lot of battery life out of it with just sending that little bit of data. Right? If you don't need 54 megabits per second, then choose something that is going to use less energy and last longer, especially if you're running it off of a battery. Alright, so the last thing I want to talk about is this IoT communication method called MQTT. So MQTT stands for Message Queuing Telemetry Transport, and it was originally created by IBM, but now it's controlled by Oasis, which is an independent group. But there's several versions. 3.11, even though it's actually over 10 years old now, is actually used quite a bit. It's usually sufficient. They do all the way up to version 5 with extra features if you need them, but a lot of times you don't need that extra features, so it just throws in overhead that you don't need. So one of the things to keep in mind here with MQTT is like any of these other communication protocols, they use ports. When we were using Node-RED, we had to go to the BeagleBone to the Node-RED service on port 1880. MQTT just happens to use port 1883, so I just keep that. It's just a coincidence they're so close. There's nothing directly related to them, but when you try to talk to the server, you will have to specify the port. Now when I say default port, that's the default or expected port, but if you're setting up your own MQTT server, you could pick some other port. The only major thing is when you're trying to pick a port is that you don't want to use default ports that are expected to be used by other protocols, and the port should be larger than 1024. All of them below 1024 are kind of reserved for dedicated uses anyhow. So MQTT you can use either unencrypted or encrypted. So again, this kind of gets into using the right tool. All right, so the MQTT system works on what's called a publish and subscription method, and so they use what's called topics, which are hierarchical structures, kind of like the files on your file system. You have slashes in between these topics, and then there's a broker. So what happens is you have this broker that devices can subscribe to when they want information on particular topics. So they have to subscribe to each topic that they're interested in, just like you might subscribe to a magazine or a newsletter. And then when information is published to that topic, then everybody who is subscribed, the broker will pass that information on to them. So this subscription, what this does is it makes a network connection to the broker. And then the broker basically then sends out this, what they call a heartbeat, which is just kind of a very short little bit of information. And that keeps the port open, that keeps the network connection open. But it doesn't use a lot of bandwidth because we're just sending a couple of bytes of data. So it's not like we're sending down tons of data every minute. We're just sending a couple of bytes every few seconds to maintain the connection for the subscribers. And so then that allows, again, when the censors or whoever publishes something to a topic, and then the broker has that communication, and so it can just send that, pass that message on to the subscriber. All right, so some of the advantages of MQTT: it's very, very lightweight. Again, it's designed just to send a few bytes of data every so often, like temperature, pressure data, or just little bits of information about the status of machines and things based on some sensors. We're not sending videos or anything like that. And it's safe communication. It's very cool because it actually allows you to do communication across the internet, across the cloud. But the catch is that if you do that, the broker must be outside the cloud. So you can set up your own broker for internal communications, but if you want to do communications through the cloud, you would have to pay or set up a broker outside in the cloud. So you maybe something like Amazon Web Services or Microsoft Azure, something like that, to set up this cloud-based broker. Okay, as mentioned before, it can work with or without encryption, and you can send as little as 2 bytes of information or a maximum of about 256 in one transmission. Okay, so some disadvantages: again, we're not sending tons of data, so you can't do like video streaming or anything like that. That's not what it's designed for. Another issue is you have this broker. If the broker goes down, it's kind of like the star format that we had for our network. If that center point goes down, nobody can communicate. Now you can set up multiple brokers so that if one goes down, you could send the data through another broker, but that adds an extra layer that needs set up. The other thing is that by default, there's no acknowledgement that the message was received. So these devices that are publishing the information, they don't necessarily know that the message was being received. So if you want them to know that, then it's up to you to set up some sort of acknowledgement message to go back the other way, which means that the publisher would also have to be subscribed maybe to some sort of acknowledgement topic, or however you wanted to set that up. But by default, there's no guarantee that it was actually received on the other end by the sender. Okay. The other piece of this is it's not for real-time messages. You're going through this third-party broker, and so the data being sent is not going to be guaranteed to get there in any sort of known time frame. So it's a very handy communication method, but it's not designed to be real time. All right, so that concludes it for this video.